Okay, so this video is going to be going over the singularity function from solid mechanics, or from machine design. Yeah, so I'm going to just go over a very basic statics problem, and then I'll show you why using the singularity function is actually really neat. So let's say we've got a beam connected to a wall. Very basic problem. We've got a distributed load, we've got a point load, and that's it. Let's say a distributed load has magnitude of 1, this has a magnitude of 2, and that's it. The whole length of the beam is 1, 2, 3. No, 0, 1, 2, 3, 4. 1, 2, 3. 0, 1, 2, 3. Okay, cool. And we're starting from the left side. So x equals 0 is on the left side. Cool. So what does this beam have? This beam has a reaction force. I'll call it F. And a reaction moment. And I'm drawing both of those such that the number is positive. Okay, so just very quickly, let's solve for F and M. So F, what would it be? It should just be 1 times 1 plus 2, so it should just equal 3. The moment is 1 times 2.5 plus 2 times 1, which equals 4.5. Cool. All right, so very easy. That is all of the problem. Yeah, okay. So what if we wanted to find, well, in the real world, this beam, if it was subject to these loads, it would deflect a bit. I'm over exaggerating it here, but it would deflect a bit. So it would have some angle, deflection angle, and it would have some displacement, so deflection displacement. But just using normal statics, we can't really calculate those two very nicely. There's like a table, and you can kind of add stuff from the table, but there's no super nice consistent way to solve for these two variables. So the singularity function lets you solve for these two variables, and it's pretty freaking neat. But the singularity function has its own set of math rules. So I'm gonna go over those first before writing out the singularity function. So, rules. So distributed loads take the form of something to the power of 0. This will make sense when I start writing it out, but I'm just writing these rules out here for now. Point loads take the form to the power of -1. Moments are to the power of -2. Okay. Now the math rules. When you integrate, I'm gonna dot these. Negative number don't bring down the negative or the number. That seems very weird, but when I go into the example, it'll make more sense. Another rule, don't evaluate negative exponents. Again, weird rule, but it'll make sense later on. Another rule. After you plug in x, if what's in the parentheses is negative, ignore it. These are very weird rules. They're calculus based, but they're just weird rules. All right, so when you're doing singularity function stuff, there's 5 equations. There's Q, V, M, I think theta's the next one. Yeah, theta's the next one, and then Y. So Q, I forgot what it's called, but it's the one that doesn't matter. V is shear diagram, M is moment diagram, theta is deflection angle, Y is deflection amount. So we're going to start with Q. Always start with Q. So for this specific example, what would the Q equation look like? So we have a distributed load of -1 because it's pointed down. -1 times x minus 0, and distributed loads are to the power of 0. So what does this mean? So this is the magnitude. This is the location at which it's applied. In this case, since it's a distributed load, it's the location at which you start applying it, and it continues being applied until the end of the beam. So I said that it starts being applied at x equals 0, and the way it's written right now, effectively, it is applied to the whole beam, not just to the first third of the beam. So in order to get a distributed load to be applied only to a certain part of the beam, you have to add a counter distributed load. So in this case, we would add positive distributed load such that it cancels out with the second, well, I guess what, the second 2/3 of the beam. So in this case, it would be -1 to the power of 0. So you're now adding a counter distributed load. So the end result is you only have a distributed load right at the front of the beam. Okay. Next, we have the point force of 2. It's a minus because it's pointed down. And point loads are -1. And then we've got a reaction force that points up. Which is also a -1. And then we have plus or a minus for the moment. I think it would be a minus for the moment because I have to put my thumb into the page for the right hand rule. -2. And it's -2 because moments are to the power of -2. I did most of the problem over here just to make sure I could do it. Okay. So that's a Q equation. It doesn't really mean anything. It's just the one that you use to set up everything. So to get to the next equation, to get to v, I'll write it lower. To get to v, you have to integrate q with these weird rules. So let's do that one by one. So we get -1 x minus 0 to the 1 plus 1 minus 1 to the 1 minus 2 x minus 2 to the 0. I didn't bring down the negative because one of the rules is don't bring down the negative or the number. Plus f x minus 3 -1 minus m x minus 3 -1. Again, I didn't bring down the negative or the number because normally this should be m over 2 and it should be a positive, but with our weird rules, it's not that. Okay. Now, because we integrated, there's a plus c1 plus a constant. So we can solve for that constant. How can we do that? Well, step 1 is to write the shear diagram for this setup. And it would be would go down because it's a distributed load. It would go across, it would jump down, go across, and then go all the way back up. Yep. So that's the shear diagram. So we can use a couple boundary conditions here. The one that you almost always want to use to figure out what C1 equals, and it's almost always going to be 0, is the point on the left-hand side, which is v at x equals 0 equals 0. And that equals -1, 0 to the 1, plus 1, -1 to the 1, minus 2, -2 to the 0, plus f, -3 to the -1, minus m, -3 to the -1, plus c1. All right, let's look at our rules. Don't evaluate negative exponents. Do we have any of those? We have, oh, I made a mistake. That's supposed to be a 0 because we integrated it. Here it's supposed to be a 0. Yep, okay, looks good now. So don't evaluate negative exponents, so that gets canceled out. After you plug in x, which we did, we plugged in 0 for x. If what's in the parentheses is negative, then ignore it. Ignore, ignore, ignore. So all we're left with is this term, which 0 to the 1 is still 0, so we just get 0 plus c1. So then we conclude that c1 equals 0. Cool. Now we can use our other boundary condition to solve for what f should equal, and hopefully it matches what we got over here. And this would be v at x equals 3 equals 0. Okay. I'm not going to write the C1 because we already said it equals 0. Let me just double check this. Yeah, it's probably right. Okay, so one of our rules was don't evaluate negative exponents, so that goes away. So we're left with -3 plus 2 minus 2, because 1 to the 0 is 1, plus f, because 0 to the 0 is 1. Cool. And this gets us, the 2's cancel out, and this gets us f equals 3, which is exactly what we got back here. So this method does work. It's more complicated for finding f and m, but it's the only real way to find theta and y. Okay, so that's v, and we have a couple more of these to go. Cool, let's do m. M is, they're all the integrals of each other. So m is the integral of f, theta is the integral of m, and so on. M. Okay. -1/2 x minus 0 to the 2. And we get a new integration constant, C2. I think this is right. If, what's the rule? When you integrate a negative number, don't bring down the number or the negative. But if you integrate a positive number, bring down the number. So when I integrated to 2, I brought down the 2. Okay, so similar to the shear diagram, on the moment diagram, I'm not going to write it out because it's more complicated, but you also start and end at 0. So m x equals 0 equals 0, m x equals 3 equals 0. And we use the left one to get rid of C2, basically. Yeah, 0, yeah, this term will cancel out. This term will have a negative inside the parentheses. This should not be a 0, this should be a 2. So that'll be a negative also, a negative, and a negative. So again, we just get C2 equal, well, yeah, C2 equals 0. Cool. And we can use the other one, the other boundary condition, to solve for m. What do we get for f? We got 3. Okay, so we get negative 9 over 2, which is 4.5, plus 2 minus 2. 0 to the 1 is 0. And then we just have a minus m. So then we get m equals 4.5, which is exactly what we got up here. Cool beans, so that all checks out. Now onto theta and y. So these two are a bit more interesting. Exact same process, except now we don't just say theta equals something. We say I theta equals the integration. So the idea is once you get a number on the right-hand side, like let's say you get 13, you divide it by EI, which is modulus of elasticity and moment of inertia, and then you get the actual degrees in radians. Okay. That would be 1/6. Minus 1. Okay. Yeah, I think that looks right. All right. Now, what are our boundary conditions? They're not 0 and 0 anymore. Right up here, on the left, if we draw like the neutral axis, we can see on the left-hand side, there is an angle. So on the left-hand side, the angle is not 0. But on the right-hand side, the angle is, there's no angle, it's 0 on the right-hand side. So we can use the angle on the right-hand side being 0 as our first boundary condition, and that would, actually as our only boundary condition, because all we need to do is solve for C3. We could leave the E and I over here for now. I'm probably just going to say each of these just equals 1. But yeah, we'll see. Okay, so theta at, let's say E I, theta at x equals 3 equals 0. Because on the right-hand side, there is no angle. So that would be what was F? F is 3. And M is 4.5. This is not going to be fun. Oof. 27/6 plus 8/6 minus 1 plus 0 squared is still 0, so that will go away. So then we just have a minus 0 to the 1 is also 0, so that would go away. And we just have a plus C3. Is that right? I think that's right. Yeah, and it kind of makes sense that these two loads, like the reaction force and the reaction moment, don't contribute to how much the beam bends, because no matter how big this force is, it won't make the beam bend anymore. But if like the distributed load was like twice as big, that would push the beam down more, if that makes sense. So it makes sense that the reaction force and reaction moment don't contribute to the theta constant. And they probably won't contribute to the y constant either. Okay. So what would this be? Negative 19/6 minus 6/6. I think that's right, but my algebra might have gotten messed up. Okay, so we get C3 is 25/6. Cool. And then if we just say that both E and I equal 1, then we can just divide this number by 1 twice, and then we get our theta equation. So theta, I'm not going to rewrite it again, but you could just plug that in there. Technically, plug it in there. And then this is your completed theta equation. Cool. And then we can solve for the deflection at, or the angle at x equals 0. So that would be, I don't know if I want to do it, but you could do theta x equals 0 equals whatever, and you just plug in 0 into this equation. I don't want to do it though. And then the last one is E I y equals, well, you just integrate it again. 24. It would be plus C3, which is 25/6 plus C4. And then we would use y at x equals 3 equals 0 to solve for C4. And then we could solve for the deflection at equals the deflection on the left-hand side. Because on the right-hand side, it's connected to a wall. There's no deflection on the right-hand side. But on the left-hand side, there would be a deflection because it's objectively lower than the center line. Okay. Cool. That is all of singularity functions. They're pretty easy, but there's just weird rules, and you gotta be careful of your algebra. But that's also like all of grad school as well. So there you go. Cool beans.